Welcome to another video explaining the universe using the particle model. Well, today's video is titled Linear Polarized Light, and this video is in response to a request by one of my viewers. I've been covering a whole list of words, laws, constants, C, three forces, not four, as I made the last time, and this is about linear polarized light. But looking at circular polarized light, and I haven't quite got that sorted out yet. It's a little bit strange, but I thought I'd go ahead with the linear part. Certainly much simpler to deal with. So we have a viewer who asked, does the particle model have a way of explaining electromagnetic wave polarization? So I said, let's start with the EM wave, and this is a typical one you see from Wikipedia. The electromagnetic wave has an electric field, a magnetic field, and it propagates along a direction X moving at speed C. Well, if you look at all forms of light, you can, here's a corpuscular model that Newton had. This is the electromagnetic wave that in Faraday and Maxwell were key in coming up with the fact that it's a combined electric and magnetic wave. Then Einstein in 1905 published his paper and said, no, I think light is a particle. And of course, you have the particle model for light, which is a stream of G1 particles moving at speed c. It has a peak or multiple peaks with a wavelength and a valley or no peaks in the middle. This is a concept that my son David and I have for the particle model. It seems that the polarization idea revolves around the electromagnetic wave and not any of these others. You might argue, well, how can you make the particle model, for example, be polarized? But let's move on and look at the what linear polarization really is, or is described. From this link, I got this picture of unpolarized light. This is the electric. Well, it's supposed to be the electric and magnetic field, but very often when they get to this point of describing polarization, this is only the electric field, and you have to imagine that the magnetic field is moving along with it. Well, but as in most cases, if you got to get this looking right. You got the electric this way, magnetic this way, and it comes out this way maybe and is moving. Not really sure about that. It doesn't say it because later it shows a little different as to how it's actually generated. But in the case of linear polarized light, when this light goes through a vertical polarizer, all of the ones that are horizontal or have a horizontal component, they get eliminated, or at least mostly eliminated, and you're left with only vertical. And then when the vertical passes through a horizontal polarizer, you get nothing. Well, you get something because these types of linear polarizers don't block everything, but they block enough that the image is virtually gone, but not eliminated. Okay, I found one of the first times I found a kind of a description of how an electromagnetic wave is generated, and it's kind of interesting, and it goes through three steps. talks first about a charged particle that is not moving, then about a charged particle that is moving at a constant velocity, and then finally about an accelerating particle, a charged particle in all cases, and thereby going through those steps, they explain how you get an electromagnetic wave. This was from University of Tennessee in Kentucky. And this is a figure I've shown a couple of videos ago with a positive charged particle which has a electric field that is outward directed in all, not just in these two dimensions, but in all three dimensions, and a negatively charged particle. In this case, the electric field is coming in. This description of the charged particle seems to emphasize this one, although it's not clear that they probably mean both, but the arrows seem to point differently. But anyway, that's a charged particle, and now if you get a moving charged particle, it produces a magnetic field. The charged particle, if it moves, produces a magnetic field. This magnetic field exerts a force on other charges, just like has been known for a long time. The force on these charges is always perpendicular to the direction of their velocity, and therefore changes the direction of velocity, not speed. That's the comment, but this is your static one that I just showed. It's a different picture, but this is where they show a magnetic field around a moving charged particle. There's a this is the circular magnetic field that you might find around a conductive wire, where you have electrons flowing through or current flowing through, and you get a magnetic field. So it has to be a moving electric charge to get that field, and it goes with it. How long it stays there, I have no idea, but that's how they say it's generated. And then finally, an oscillating charged particle. A charged particle oscillating about an equilibrium position is an accelerating charged particle. Here's a charged particle, and it's oscillating about an equilibrium position, which is the origin here, and it goes up and it goes down, and presumably the electric field goes up and down. Why? Because this charged particle is moving up and down. At least this is their explanation. It's not mine. It's theirs. And if it's moving at velocity c in this direction, this particle creates a magnetic field along with it. And so my interpretation of this explanation is that you have to have somehow this charged particle has to be oscillating up and down, and it has to be moving at velocity c, and you get this traditional version of an electromagnetic wave. Now, from the source, you can have multiple charged particles, some going up and down, some going left and right, some going at an angle. And again, they're only showing the electric field part. Here it goes through a vertical polarizer, lets the vertical through, and the horizontal detector. Well, this is a detector, horizontal or not, and it detects this. For a horizontal polarizer, you have this, but it's kind of odd. Every time I went to find this horizontal, in fact, it's used quite often. They have a horizontal polarizer, but it lets the vertical through. This is wrong. This is supposed to be this is supposed to be horizontal, and this is supposed to come out horizontal. It gives vertical again. This is vertical. This is horizontal. this should have a horizontal wave coming out, not a vertical wave. In any way, this is the basis of polarized light. This is unpolarized because it's random number. You can have over a very short interval of time, you have a lot of charged particles up and down, left and right, individually going through and being either vertically polarized or horizontally polarized. Well, the particle model for light I showed you earlier is the stream of G1 particles moving at speed c, and it has a pattern to it, and it has a series of peaks and valleys. I don't show that here, and this is what I call what they would call non-polarized light. These are just streams of particle. They're coming at you. This is coming toward you, looking, and these are just a whole bunch of light coming from the source. When it goes through a vertical polarizer, now vertical polarizers can be mechanical or chemical. Iodine is often used as a chemical blocking means, and so these are the ones that come at this barrier get blocked. These get through, then get blocked, get through, so that you now have a layered light here. This is unlayered. This is vertically layered. And this is horizontally layered. Very simple for the particle model to do linear polarized light. This is used generally in two applications. The first application people use polarized light for is with linear polarized glasses to cut down glare. And the problem with these is that you have to keep it in line with the glare. If you get unpolarized light hitting a smooth surface like water, this light, the horizontal light, will reflect off the peaks of the water and come at you. And this is white light that is literally reflected like a mirror coming at you. And if you're wearing glasses that have vertical striping, it'll cut it down because the glare is horizontal. And yeah, you get some glare through, but a lot of it's cut down. But the rest of the light, what you want to see, the lake and the ground around, and even the fish underneath, you can still see. So polarized glasses are vertically striped. They get rid of glare from the road or from water. The other application is for 3D glasses. You can wear these. This is an interesting video showing how unpolarized light goes through a vertical polarizer. And it comes out vertical, and you can take a different one and go through a horizontal. This is two different pictures. For 3D, they got two different source of films, and they're offset just slightly. They're not the same one. They're offset slightly because they've been taken from the perspective of your eyes, and one camera sees from one angle, and your left eye sees from the other angle. And so what they do then is they take this film, and that's for the right eye, for your left eye, and I'm using this as an example such that you get horizontal video for your left eye, and you get vertical video for your right eye. And so what happens with the glasses is that if the light is coming out of horizontally to your left eye, it gets through. And if it's vertically, the vertical gets through. But in fact, both of these streams of light hit both lenses. And so the vertical, when it hits this, is going to get blocked, or mostly. And the horizontal, when it hits this lens, is going to get blocked mostly. So your one eye sees the right eye sees the right part of the picture, and your left eye sees the left part, and then your brain puts it together, and voila, you have 3D. This is pretty well unknown. I just wanted to relate the vertical and horizontal polarization. It's linear. And it turns out if you tilt your head a little bit, you kind of lose the 3D. So you're kind of forced to keep your head straight with these types of glasses. Well, it was Christmas on Christmas Day, 2015. My wife Pat, my son David, and I were at the Kennedy Space Museum on that day, and we went to a theater to watch a 3D movie. Well, Dave and I had been talking about polarization, oddly enough, and so when we went, David decided to do an experiment while watching the movie. He closed one eye and carefully looked to see what was there. He looked very carefully through the one eye, and he saw both images. You got to watch, you got to just study it. The main image was strong. The other image was slightly offset and was quite weak, but you can see it. So some of the image got through, and I don't know whether these were linear polarized or circularly polarized, but that's another story. But it's just to point out that it isn't completely blocked using linear polarization. Well, circular 3D, I said at the beginning I didn't have this quite figured out, and apparently circular polarized lenses work at any angle, and you can watch videos where they tilt the glasses and they got light coming through, and it's not blocked. It works no matter which way you put them. Haven't been able to figure that out yet. That's a little bit confusing, and what happens is they have to generate this circular polarized light. I'm not going to go into it, but this is a typical picture of it. But there's a 3D movie. You might want to. I'll list this in the description of this video, but and it's really not a scientific, really a good explanation of everything, but it has some interesting graphics that are easy to watch. Towards the end of the video, he's showing you that you got two cameras, one with a film for the right eye and one for the left eye. And the output of these, the film goes through a circular polarizer and creates that signal I just showed you. One rotating clockwise, the other one rotating counterclockwise. They hit the screen and they come back to your glasses. And this is the right circular polarized light and the left circular polarized light. Just like in linear polarization, they both hit, but they show that the right on the right eye gets through and the left doesn't. And here again you have right circular polarized light and left circular polarized light. The left one gets through and this one gets blocked. Not at all clear. Don't understand how it's blocked. Just to say that it is doesn't give me the answer. What I'm really needing to find is how how they generate and how they what they use to generate the polarized light and what they use here in the glasses that causes it to be blocked or not. Never found it. I'll look. Could ask my viewers for help. Maybe somebody really knows and understands this real well. Send me an email at particleguru@gmail.com and appreciate the input. So at some time when I get this figured out, I'll come back and talk about why circular polarized light can work at any angle and block. Just I need more information about how it's generated and how this is made. Oh, well, yeah, this is the big question. How? I'm just jumping ahead about how do they get blocked? My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle. Contact me at particleguru@gmail.com. Thank you for your attention.